Excellent. Okay, so you guys, like I say, you already know all this, but we will quickly review it. Because it needs to be reviewed, because as Taylor said, even though she is a brilliant math student, she has a bugaboo about exponents. Sorry to name names.
No,
but she made a big deal out of it 2 seconds ago, and everybody around her heard it. She freaked out.
I can confess it. I am not good at this.
Yeah. So it's good to re-up it, because it's not basic in its complexity, but it is basic in its application to further mathematics, meaning that a lot of math is built upon these few principles. So you do want to be good at it. So let's start. Powers are used to represent multiplication, repeated multiplication, which you already know. Multiplication is just repeated division, is just repeated addition, right? So obviously we need to do something to repeat multiplication, which is exponents. So the entirety of exponents is based on the simple understanding of that expression. What does that mean? Do not tell me anything that has a number bigger than 7 in what you're about to say. What does that mean? 7 times 7 times 7. If you understand that, like actually really understand that concept, then everything else is built on that. But a great many of you still will tell me that that answer is 21. Or you refuse to actually commit that into your mind and learn it and live it and love it. Because being the cream of the crop of math students that you are, very often you think that, oh, I got the basics. I don't need to worry about them again. And yet, still, I have students in these cream of the crop classes that are like, okay? And I don't want I want, yeah, buddy. Get the difference?
Yeah, buddy.
There you go. All right, so let us start by reminding you of what all these things are. Real simple. The base, I'm going to highlight in yellow. And I'm going to come over to this thing right here, and I'm going to highlight the base in yellow. Now, again, what is the base? Do not tell me a number. Okay? Do not tell me a number. Think about what I just asked you, and think of how you would answer me. Gurpinder.
Like the number that's bigger, like in terms of size.
Like in actual physical size.
Yeah.
In that this 7 is taking up more real estate on the page than the 3.
No, like, I mean, like, okay, never mind.
Because, well, the only reason I ask is because what if I asked you this? Then what's the base?
Yeah, you can.
Right? Okay. But if you meant actual physical size, then yes, absolutely. The way we write a power, the number that is physically bigger is the base. Fine. Taylor.
The number that's being repeated a certain number of times.
All right, that's more what I was looking for, mathematically speaking. Okay, so mathematically speaking, yes, the base is the number which is repeatedly multiplied, which you all already know. Now, the biggest problem with that is all of you know that. You get that already. The problem becomes not all bases look that pretty and perfect. And this is where you guys fall into problems. And this is where Gurpinder's definition is actually very useful to us. Because while it is not mathematic by any means, it's the bigger number. She's just looking at sheer size. It's actually important to notice that. Because that tells you what the base is. So physically speaking, the base is bigger. And I'm going to add another thing about its physical location. It is only what is left of an exponent. Now, that's wonderful because the exponent I'm going to highlight in blue, and highlight the word in blue. Because, yes, it's easy to say, and every math teacher says it, if you're looking for the base, just look to the left of the exponent. Which is great if you know everything about it, if you know what the exponent is. But sometimes you do not. So, and then they usually define the exponent as being whatever's to the right of the base. See the problem here? So, let's talk about the exponent. What is the exponent? Again, I don't want to hear a number. What is it? Leighton.
The number of times you're going to multiply the base.
Right. It is the number of times you multiply the base. Now, again, that's what it is, but again, it's the smaller number. It actually has a name. If you've gotten far enough in chemistry, you know that a little number below the line is a subscript. This guy is a superscript. Right? And the exponent is always to the right of a base, which I'm going to highlight in yellow because I want to keep all that going together. All right? Now, those two concepts are very easy to understand, yes? Okay? If Leighton is the exponent, then who is the base? Avipol or Blake, from your perspective? From your perspective. Leighton is the exponent. So who's the base, Blake or Avipol? Is everybody happy with that? So from your perspective, Avipol is indeed the base. From my perspective, who is the base? Blake. Excellent. So everybody can find it. Yes? All right. Now, Michael, do me a favor. Put your arm out like that. No, your other arm. There you go. Avipol, put your arm through Michael's arm. Link up. Like we're playing British Bulldog.
What?
Everybody remember that game? Probably not, because you wouldn't have been allowed to play it because it required touching, and that's not allowed.
Never even heard of that game.
I don't know what they call these games now. They don't even call pig in the middle anymore. Monkey in the middle, because you don't want to call a kid a pig. Meh. It's okay to call him a monkey, but you can't call him a pig.
In elementary school because I have really hairy arms.
Anyway. Now, what has happened to the base? It is linked to something else. Right? So the base need not necessarily be one thing. Thank you, gentlemen. Does everybody understand? And this is where the confusion sets in. Because if I write something like that, no problem. Everybody knows what the base is. But as soon as I start monkeying with that base, or pigging with that base, see what I did there? We get into issues. So we're going to leave that alone for now. The whole thing
Oh my goodness, that scared me.
is a power. The power, speaking of power, just for fun, guess who my son's fight coach is on the 100?
Who?
No, the pink Power Ranger from the movie.
Oh my god! Which pink one? Like which Power Ranger movie?
The pink one. The last one.
Like the newest one?
I guess so.
What?
She was also a Ninja Turtle. She is the one coaching my son for his fight scenes. Which, by the way, he is literally kicking ass at because of all of his
And he's also doing well in them too.
all of his karate. Yes, he is both literally and figuratively kicking ass.
Way to go.
Anyway, the power is the whole thing. It is a base and an exponent. And we read it as 7 to the third. Some of them get special names. The third, we say cubed because we're lazy. The second, we say squared. Nothing else gets a fun name. Okay? All right. Now, fill this table in. There are some tricks. You know this from the 9th grade. You may need to talk to your neighbor. Go carefully. There are some tricky ones in there. Go carefully. I'm going to shut this off so I can write a few down without you copying along, even though I know you guys would never do that. Whistle, whistle, whistle. Guys done yet? Guys done yet? All right. As promised, this chart actually has everything you need to know to do very well in this unit. 2 to the 4th, 2, 2, 2, 2, 16, right?
Yeah.
Easy peasy lemon squeezy. Next one. What is it?
-3.
The base is 3. Negative 3, 3, 3, 3, negative 27. Why is the base only 3? I can quite plainly see I have a negative there. Taylor, who is bad at exponents.
Well, this part I get, but like when you start adding all anyways. So this part, okay, it has to have the brackets around it because that's just 3 to the power of 3.
Right. The
Like it's
base.
not -3 to the power of
It's
3.
Right.
-1 times
It is technically -1
Yeah.
times 3 to the 3rd.
Yeah.
The
You need to have
base.
the brackets there.
Yes, the base is only what's attached to the exponent. Okay? I'm going to take that one step further. X plus 7 squared. What is the base in that expression? Close. No. X and the base is anything to the left of the an exponent.
X plus 7. No,
No.
it'd be 7.
X and 7 are both bases because x has an exponent, doesn't it? Okay. What is x plus 7? Now what's the base? X plus 7. Okay. All right. Excellent. This one. Why is the base -5? Because it's in brackets. So it is -5 times -5, which is positive 25. Yes?
Yes.
Excellent. That one's easy. 32,768. The question here is, do you remember how to evaluate those with your calculator? It is the X to the Y button. Or it might be a little mountain, or it might be Y to the X. Or in the newest iterations of calculators for people that are really, 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 really bad at math, it's X to a blank. Or if you're really bad at math, I've even seen lately blank to a blank.
But that makes it harder.
Well, mine's X to a blank.
I know, because you people understand math. But regular people on the street, X and they put the alphabet in math. Those, so they say blank to blank, which is because every one of you kids understands this question. I have 3 apples. There's a pile of 10 apples there. How many apples must I add to have the same amount of apples as that? All of you can do that, but as soon as we put a letter there and call it algebra, but there's no need to be scared of algebra because you've been doing algebra since kindergarten. But your teacher didn't call it algebra. They didn't call it algebra until grade 10, and then everybody's like, oh, or grade 8. Everyone's like, oh, I hate algebra. I'm so bad at it. But you're not. What?
We were playing earlier today in my chemistry class. We were playing Kahoot, and we did a first grade math one, and people were getting the answer wrong.
Doesn't surprise me even the slightest.
It was grade 1 math.
It doesn't surprise me in the slightest. Pretty much exactly what you learned in grade 7, except it didn't have as cool a name. That's the problem. All right, let's move on. Whoa. All right. This one's tricky. The -1 repeats every time, right? Negative, negative, negative. So it has to be part of the base, so it must be bracketed. But here's where something that bothers Taylor comes into play. What? -1 times -1 7 times is still -1, right? Yeah. What is -1 8 times?
1.
That's going to be +1. But what is -1 to the 8th? -1. What is -1 to the 7th? -1. But is that the same as that?
No.
They're the same value, but they are not the same thing. Because what is the base here? What is the base here? Oh, so smart. 10 cubed, easy peasy lemon squeezy. What if it was 10 to the 7th? How many zeros would there be? 7, which would be 1 and 7 zeros. 10 million. Well done, Leighton. What's different here? It's x. Can you tell me that? No, why? Because you have no value for x. Brilliant. Now, this is the first really tricky one. Base of positive 2, exponent of 5, but a value of negative 32. Had to be a positive base with the negative right there. But what is this? What does that equal? Also negative 32. But does that in value equal that? Yes. If I were to ask you to define all the parts, would you say they were the same? No. Oh, you guys. Now, I left this one blank. Why? I left 2 of them blank. Yes. If you want to do the base of negative 3, turn to page 74. If you want to do the base of 3, turn to page 32. Do choose your own adventures still exist?
Yeah.
Shut up your face.
Okay.
Really? I only ask because I recently came across I don't know if you were in my class, but at one point at this school I said, you know what somebody should make? Somebody should make a grown-up choose your own adventure.
What is choose your own adventure?
And then last year, cruising through the library on my iPad, I came across somebody's done it. It's a choose your own adventure for grown-ups. So it's like you were out drinking last night. Do you call in sick to work or tough it out and go in? And it was choices like that. And it even had the same old-fashioned cover like the old choose your own adventures with the red oval on the top. And it was just like that.
In elementary school, we have a drawing section.
Yeah. Of course you did. So did I. And then you die, and then you go back like 5 choices. Yeah, I know. Anyway, so as Lauren has said, to take us down a road on memory lane, we are going to choose our own adventure. We could, I bet almost all of you wrote 3, 2, and 3 times 3. I've been doing this for 1 or 2 times. Now, some of you may have said, oh, Mr. Myers, negative 3 and 2. And then maybe you did negative 3 times negative 3. Oh! In which case you would have 3 squared, or you would have negative 3 squared. What would you not have? Negative 3 squared. Right? Right. Yes. Would you just let me get there for a moment? Now, a great many of you might have said, nah, you can't fool me, Mr. Myers. And you did the red one maybe. And then you said, well, I'm just going to do the green one down here. But then, of course, I would say, but what about?
9 to the power of 1.
9 to the power of 1. I could have had 9 to the 1. Oops. 9 with an exponent of 1, which would just be plain old 9. And I would write it as 9 to the? Nothing, because we never write exponents of 1. You kids. Now, could there be a negative anywhere in there? And get a value of positive 9? No, of course not. All right. Next one, tricky. The base is negative 4. Negative 4 repeats 6 times, which is an even number of times, which means it must be a positive answer, yes? Except there's a negative out in front. Dun, dun, dun. So it's negative 4,096. And then the last boring one, just to, when your brain is like, throw you an easy one and everyone's cool. Yeah? Everybody should know all of this from the 9th grade. There should be nothing new on that page. None of you should have gone. You're allowed to do this. Oh, yeah, I totally knew that. But you're not allowed to do this. No way! Understand the difference?
Well, Mr. Hirschman never taught us why the brackets made it so that you multiplied it negative 1, negative 1, negative 1. He never explained to us why you would put the negative 1 in front of it. And if he did, I either wasn't there. Well, I remember. I don't remember that. You must have been sleeping that.
All right. Again, regardless of that past experience, you're now all up to speed. Aye? Now, if you actually... Yes. Of course you can. It's that time. Yes, it is.
I'm sorry, Angel.
You are all up to speed now. So let us go on to what starts to cause problems. But it doesn't cause problems if you actually understand exponents. So what we are going to do here is something I did last year with my grade 9s, but you are going to see it again. I showed you, and I only tested you on things with numbers. But of course, you guys are all aware, math with just numbers was like so grade 6. Because now we use letters. As I was saying earlier to Lauren, oh my God, you put the alphabet in math. I actually have a little button that says that. It says, and then the devil said, put the alphabet into math. Which is pretty funny if you follow that line of Judeo-Christian thinking. But if you don't, it's still kind of funny because, of course, the devil is supposed to be the embodiment of evil. And it would have been him that put the alphabet in math. Or her. I don't want to assume the devil's gender. But since it is a supreme being, it has no need of gender. So really it doesn't matter what gender you assign to any supreme being until you call God she. And then everybody goes ape. But that's another story for another day. That's for philosophy class, not math class. My grade 6 teacher called God she. Holy Toledo did people get mad at her in that class.
Why? Because she called God a she?
Yes. But that lady was taken hostage in the Congo and fought her way out.
Your math?
My grade 6 teacher. She wrote a book about it. She was taken hostage by death squads in the Congo and got out.
Seriously?
I can't remember.
And she's a grade 6.
She was a grade 6 teacher. Now she's, I don't know, Rambo. You got me. She got out. And she wrote a book about it. Miss Sanger knows her. Ask Miss Sanger.
Who's Rambo?
That was your teacher?
What?
That
Amanda Lindhout is like 31 years old. How could she have been my grade 6 teacher? Ugh! My grade 6 teacher was named Donalda Reed.
There's Mona House in the Sky, the book.
That's Amanda Lindhout's book.
Yeah.
Wait. So this happened after you got your before?
After.
Oh.
She taught me in 1986. Sometime after 1986, she was in Africa. She was taken hostage, and she got out.
How?
I don't know because I haven't read the book. Because I have a memory of Mrs. Reed as being a lovely, awesome person who could do anything. I don't need the violent, gross proof that Mrs. Reed was a lovely, awesome person that can do everything. Okay? I don't need to know what happened to Mrs. Reed in the death squad camp because I know what happened to Mrs. Reed in the death squad camp. Okay. Anyways, I don't even know how this happened. Oh, right. She's the one that said God was she and everybody got mad at her. So let's carry on. We are going to multiply powers of the same base. In grade 6, grade 9, you did this way. If you understand what is happening, you know what is really happening. 2 squared times 2 cubed. What is actually happening there? What does that mean? 2 times 2. What does that mean? 2 garumph. No, garumph is not a word. It's not like derp.
Oh. Also, it doesn't look like a grump, it looks like a 2.
2 times 2 times 2. Now, how many 2s do you have there?
5.
2 to the 5th. Now, one of the number one mistakes made by children everywhere, including honor students, is when I say 2 squared times 2 cubed, they think the answer is 4 to some power. 2 times 2 is 4, Mr. Myers.
That's YouTube thing.
It is.
But when you write it out, actually, again, understanding the concept, not looking at the numbers, when you understand the concept, you see that you do not change the base because there are still 5 2s there. Yes?
I thought that was pretty basic.
Well, I thought it was acidic. Ah. All right. So now, as always, same thing we've been doing to you in math since the first day you learned your first 1 + 1 = 2. We put the alphabet in math. Any number to any base, exponent,
Yeah.
times that same base to any other exponent is the exact same thing as keeping that base and adding the exponents. That's the rule. Nay, it is not a rule, it is a law, which means it is always applicable everywhere in the universe of which we know that does math. Okay? Yes, I know. All right. Now, in the 9th grade, we divided powers of the same base. 2 to the 4th divided by 2 squared. In grade 3, when you were first introduced to division, that's how we wrote it. But now we almost never use that symbol. What do we use? 2 to the 4th over 2 squared, which is divided by. What does that mean in reality? 2 times 2 times 2 times 2 over 2 times 2. What is 2 divided by 2? 1 times. What is 2 divided by 2? 1 times 2 times 2. 1 times 1 times 2 times 2 is 4. Would we ever write 1 times 1? No. So we are left with 2 times 2 = 4, which we would also never write because math guys are lazy. What do we write instead? 2 squared. And the law is x to the a over x to the b equals x to the a minus b.
I see what's going on.
Aight. Raising an exponent to an exponent. 2 cubed squared. What is the base? 2 cubed is the base. So what does this mean? It means 2 cubed twice. Now what's the base? 2. So what does that mean?
2 times 2 times 2 times 2 times 2 times 2.
Would a math guy ever write that?
No.
What would the math guy write?
He would write 2 to the power 6.
Which lets you know that the law is x to the a to the b equals x to the a times b. Now, I'm going to stop there for a moment, and I'm going to ask you to put down your pencils for a second so we can talk about some of the permutations of these laws, because they are indeed laws. But, as all laws, they are subject to interpretation. Yes? So let us do some interpreting. Do not write. Think. Especially if you had trouble with this in the 9th grade. Let's start with an easy one. 2, not 2, we've been using 2 all the way along. 1.7 squared times 1.7 cubed. What's the answer? 1.7 to the 5th. Excellent. Looks different. Doesn't matter. Good? Lovely. 2 squared times 4. Is there a law for that? Of course there is. What is 4? 2 squared. So isn't that 2 squared times 2 squared? Which is what? 2 to the 4th. Lovely. Well done. What about negative 2 squared times, go away, times 2 cubed?
Well, the base there is
What would that one be? Negative 2 to the 5th. Is everybody okay with those permutations of the first law? Excellent. Do those all apply to the second law? Excellent. What if, in the second law, since you all agree that applies, what would this be? X to the 3 divided by x to the m. X to the 3 minus m. Can you do any more with that? Not unless you know what? What m is. What would happen if it was x to the 3 over x to the negative m? X to the 3 minus negative m, which is the same as 3 plus m. Is everybody okay with all of those permutations? Excellent. And finally, what if I had a 3a all squared? What's the base? 3a. So it's 3a times 3a, which is 9a squared, because the exponent goes to the entire base. Is everybody good? Excellent. Pick up your writing utensils again, and let us move along, cabbages. A fraction with an exponent. 2/3 squared. What does that mean? 2/3 times 2/3, which would be 2 squared over 3 squared, which would be 4/9. What's the rule? X over y to the a gets me x to the a, y to the a. Now right here, I have to put in a little piece of reminding tactic. All math rules apply always. What do I mean by that? What if I had x squared over y squared to the 3? What would the answer be? X to the 6th over y to the 6th. Because every previous law still applies here. Good. You're brilliant. What is an exponent of 0? So what does that mean? What's the base? What's the exponent? So how many times am I going to multiply itself by itself? You're not. You're going to do it 0 times. But Mr. Myers, everything times 0 is 0. How can it be 1? Explain. Lauren.
Like in when it's the negative, like in the second example on the chart, the negative 3 to the third, it's actually negative 1 times 3 to the third, so then the 1 is always there, basically, so you put the 1 in because it's
Excellent.
there.
Excellent way to explain that. I like that. That works nicely. Lauren is saying there is always a times 1 here. So if that can't exist, because it doesn't make much sense, does it? That 1 is still going to be there. Agreed? Great, I like that. Can anybody have another definition for it? Because there's another way to prove it. Aww. What is 3 cubed? 27, right? What is 3 squared? 9. What math happened there? I divided by 3, because that's 3 times 3 times 3, that's 3 times 3, right? What's the next logical exponent? 3 to the 1. So what should I do there? Divide by 3. What's the next logical exponent?
3 times 2. Divide by 3. Oh, it's a 1.
If it happens once in math, how often does it happen? Every single time. Now, here's another little math tricky McTrickleton. What is negative x? I lie. What is x to the 0? 1. What is negative x to the 0? Negative 1. What is negative x to the 0? 1. What is negative x to the 0? Negative 1. Does everybody understand? Every base. Okay, let's do one more. What is 1,732,364 to the 0? 1. Everybody cool? Everybody cool with y?
Yeah, I understand why.
Excellent. Don't ask me why. You don't understand. Everybody good? 1 to 5 is easy peasy?
Yes.
All right.
I understand so far, but then we get into
Turn the page over.
No.
Number 6. There it is right there. With numbers 2 times 3 squared. What does that really mean? It means 2 times 3 twice, right? There's a lot of ways we could write that, though, based on our previous laws, yes? We also know that's 2 squared times 3 squared, based on the division law, right? We also know, based on bed mass, that is 6 squared, isn't it? So all 3 of that equals 36, right? So how do we put that into law form? I've got it right here, but for some reason I hit M instead of A. XY to the A equals XAYA. Do all previous laws apply? So what if it was XMYN to the A? What would it be? X to the M times A, Y to the N times A. Is everybody good to there? Do all previous laws apply? Yes. Now this is where Taylor will shed a quiet tear. Because now we're getting funke. This is where we get into trouble. And you will notice I've left a lot of white space here, haven't I?
Because we need it, because it's dreadful.
Let us start with what exactly a negative exponent is. Let us write it down. 2 to the negative 2. What does that mean? It means, no, you are telling me what the answer is. That isn't what I asked. What does that mean? It
divided by 2, I don't know anymore.
it means 2
Yeah.
times itself negatively twice. It is not possible, is it?
Exactly.
It is impossible. But math always makes sense, yes?
No.
Yes, it does. 2 squared is what? 4. 2 to the 1 is what? 2. 2 to the 0 is what? 1. Yes?
Are we going to just keep going?
Of course we're going to keep going because math is always logic. What is the next logical exponent? 2 to the negative 1, which means what do I do here? What's 1 divided by 2? 1/2. What's the next logical exponent? So what do I do with 1/2?
Divided by 2.
If I have half a pizza and I cut it in half, what do I got? Quarter. What is 2 to the negative 3? 1/8.
It's like halfway. But 2's an easy one. Does my calculator tell me these things? Yes, it does.
No, because your calculator won't give it to you in fractions. Your calculator will tell you this answer is 0.0 or 0.125. Some calculators will. Everybody good?
Yeah.
That's all that's happening. Now, that helps some people. And being the good math teacher that I am, I want to help as many people as possible. So I also show you this. What is 2 squared divided by 2 to the 5th? You already know that law. What is it? It's 2 times 2 over 2 times 2 times 2 times 2 times 2. Yes? What happens here? Gone. What happens here? Gone. What's left in the denominator? 2 cubed, which equals 8. What's left up top? What's the number we don't write? 1. 1. Because if it was 0 up top, what would 0 divided by 8 be? 0. And we quite plainly can see there are no zeros here. The base is 2. There are no zeros involved. Got it? Great. Now, of course, we can write out our law. X to the negative a equals 1 over x to the positive a. Now, this one has the most permutations, which is why you have so much blank space. Remember, all laws apply. What is this? 8 to the negative 2. Does that make sense? First thing you ask yourself, is it possible? No, make it possible. 1 over 8 squared, which is 64. Excellent. Can everybody do that? Great. Next logical step is this. X to the negative 2. What's that? 1 over x squared. Excellent. Can we evaluate it? No, of course not. Next logical step. What is this? 1 over 8 to the negative 2.
8 squared.
What's not allowed? Not allowed to have a negative.
Yeah, flip it.
What was this guy originally, really?
8 over 1.
So what does this guy become?
8 over 1.
8 over 1 squared, which is 64. Everybody good still? Okay. What would this be? X over y to the negative 2. Really? Where does that negative 2 go? Everything. X to the negative 2 and y to the negative 2.
So it's y squared. X.
Y to the positive 2 over x to the positive 2. What's the shortcut? When I have a negative exponent with a fraction, I can just turn it over, yes? Okay. Next logical step. What is x to the negative 2 to the negative 3?
1 over x to the negative 2 to the negative 3.
That is following all the steps. Sarah, what is it? Say it again. 1 over x squared to the negative 3, which would be Yes, you do. Follow all this. Doesn't this
Flip again?
look like this?
Yeah.
So what would it be? Lauren, help her out.
1 over x to the 6th.
X to the 6, not 1 over. Because that negative exponent does what to the fraction?
Flips.
Flips it. That changes that exponent to positive. Now I have x to the 6th. Good?
Yeah. I don't think you could do that, wouldn't it? I thought it would just be negative.
Next logical step. 3. I lie. 30 x squared over 60 y cubed all to the negative 2.
Flip the entire thing.
Why do I flip the entire thing?
Because they're together.
Okay, so I'm going to flip that because of that. 60y cubed over 30x squared to what power? 2. Excellent. Now what?
You do the law.
All math rules apply. So bedmass is right happening here, isn't it? What is 60 divided by 30?
20. Oh, 2.
2. Y cubed over what? X squared. All of that squared. Now what? Where does that 2 go? Everything. What's 2 squared?
4.
What's y cubed squared? Over?
X 4.
Done. Following your regular laws from the first thing you ever learned about repeated math, bedmass, up to the last thing you ever learned about repeated math, 7 exponent laws.
This
Must,
is the last thing we'll ever learn about repeated.
pretty much. Huh?
We'll never say that.
This is about the extent of add, subtract, multiply, and divide.
It's basically
After-
gonna be like the same thing since elementary school.
Yes. This could have been taught to you in grade 3 if you actually memorized your times tables, couldn't it?
Bash, yeah.
And if you ask kids from many other countries in the world, when did you first see exponents? Grade 3, grade 4. You guys saw exponents in grade 6 when you did Pythagoras, right?
Pythagoras in grade 6?
Yeah, I did.
Okay, regardless, you saw it.
Yeah.
And then you never went past 2, did you?
We did cubes, that was it.
Oh, you did some cubed?
In grade 7 we were doing bedmath, we learned exponents.
Yeah. But they were always little exponents, right? 2, maybe 3.
Sometimes it was like 30 and
Good. You had a good teacher. All right.
I still don't know what times tables.
I know. It's nothing, it's not a problem though. Now, there are, as I said, permutations. But can those permutations get around the laws?
No.
No.
It'll be locked up.
So, x to the negative 2 over 3 all to the negative 3. Apply laws in any order you wish to tell me what that is. I do not recommend attempting it in one step.
Keep flipping.
Oh, it'd be x to the power. Okay.
It's funny when Sam is at something that he is not totally comfortable with, because if Sam is totally comfortable with, he is the first person who race Amshuman to yell out answers and not let people try it. I know.
Did they do it?
No, it's
Talk amongst yourselves. Stop being honor students. Be collaborative.
Hey, Lauren, what'd you get? I'm just gonna stay my answer. That's all.
Why is this question so difficult to work collaboratively on? Why is everyone arguing? You do know how to do it. There's a lot of different ways you can do it. And you guys have all been brought up. There's a way to go about doing math. And there just isn't. So, here's a few things I could do. Could I use law 3? Look back on law 3. What does law 3 say?
Raising an exponent to an exponent.
Does this have an exponent to an exponent? What is 3's exponent? It's 1. Do I have exponents to exponents? So could I use law 3 right away? Okay, so let's use law 3 right away. What do I do with 2 and 3 in the numerator? What's negative 2 times negative 3? 6 over 3 to what power? Negative 3. Because 1 times negative 3 is negative 3. Now, what is the next law that I can apply to? Do I have any of the same bases?
No.
So every law is out the window up to law 7. What is law 7?
You gotta flip it.
Negative exponents. What has a negative exponent? The 3. So where does it go? To the numerator and becomes positive 3 x to the 6. Would we ever leave that? No, because that's not simple. How much money is it to get into this movie? It's 3 to the 3rd power in dollars. No, it's $27 because that's what's simplest. 27. Well, of course you're taking your date and you're paying because you invited. Duh.
I don't have any friends that really go out with me, so.
X to the 6. Now, yes, Lauren.
Where did the division go? You can't divide because you got different bases. But like, I wrote 27 over x to the 6th.
So how did x to the positive 6 end up as a denominator?
Because I flipped it over.
We'll talk about that in a moment. Following this string of laws, whether you followed these laws or not, does it make sense?
Yeah.
Excellent.
It doesn't make sense.
Lauren, you followed a different string of laws. I'm going to show you right now.
But even looking at this, it doesn't make any sense.
Okay. All right. Okay.
What division?
Are you okay to hear?
Yeah.
All right. Now, this is saying x to the 6th divided by, right?
Yeah.
1 over 3 to the positive 3, yes?
Yeah.
Because 3 to the positive 3 is this, right?
Yeah.
Now, when you divide fractions, 1/2 divided by 1/8, what do you do to the second fraction?
Oh, you flip it. Okay.
So what do I do to that second fraction?
Flip it.
Flip it, so it becomes x to the 6th times 3 to the 3rd over 1. What's x's denominator? 1. 1 times 1 is? 1. Denominator of 1 we never write. Up top, 3 to the 3rd times x to the 6th. Cool?
Okay.
All right, now, am I locked into this line of thinking? It all makes sense. Do I have to do that, though? What if I applied law 7 immediately? What's the base in this expression? What? All of this is the base, yes? Any base to a negative exponent does what? Reciprocates. So isn't this 3 over x to the negative 2 all to the 3?
That's what I wrote.
Okay.
But I got it wrong still.
Just
Okay, I'm so sorry.
now, what here don't we like?
X is got a negative.
You might not like this. We're sticking with exponent law 7 this time, aren't we?
Yeah.
So I don't like this. Where does a negative exponent go?
The other side.
To the other position.
Yeah.
So this becomes 3, which was already there, and I bring up x squared, yes? Because he's negative and now he's positive, which means what? What? We're only dealing with the brackets right now. What is the denominator now? 1. Do I ever write 1 as a denominator? I'm going to leave it there because we're thinking. Now what is all that? Cubed. Now, exponent law 3. Power of powers. Where does that 3 go? To the 3. 3 cubed. Where does that 3 go? To the x squared, which is x squared, x squared, x squared. Yes? 3 cubed, 27. Squared, squared, squared is how many x's? X, 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 x. X to the 6th. Apply the laws in any order, but apply them consistently. And apply them. Do not go blah, 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 this, blah, blah, blah. Follow it through with each law with which you wish to apply. Yes.
I didn't like, when I got to that 3 over x negative 2 with the power of 3, I actually wrote it out, like, instead of as a fraction, like 3 divided by 1 over x squared. Yeah, divided by 1 over x squared.
Mm-hmm.
Yeah. And
Then all that cubed.
all that cubed.
Okay.
And then since it's division, and like I cubed it first, and then
3 cubed over 1x to the 6th.
Yeah, and then
Remembered that that's divided by, so it becomes 3 times x to the 6th over 1. Well, 3 cubed.
well, yeah, and then you get this.
Then you get, again, lo and behold, the same answer. 3 cubed times x to the 6th over 1, which is 27x to the 6th. Why you guys don't like exponents and why you continually make mistakes at them is because for the first time ever, you are being left up to your own devices. You take your math knowledge and apply it to a situation. Until grade 9 or 10, your math teacher said, here's how you do it, now do it. And now that you are allowed autonomy, you are scared because there is more than one way to get there. And you get tripped up because you do not have actual mastery of the original concepts. Because you were allowed to shuffle your way along without ever gaining that actual mastery for a variety of reasons, all of which are bad, in my opinion. But I don't make those decisions. Your job today is to complete all of the easy page of exponents, which for you guys, I believe, is 103 and 104. Other way around, 97 or 90, 97 and 98. That is your job. Tomorrow you have a trigonometry test. Tomorrow you have a trigonometry test. It will take, as usual, the entire period. Your class tomorrow is at the end of the day. By design. Aye? Aye. On Thursday, we will pick up with exponents on more complex examples. On Friday, we will pick up with exponents with I am lying in the corner crying in a puddle of tears exponents.
But I
Okay?
don't like that.
I know. So you'd better really build up some thick skin between now and Friday by doing all this practice. Okay?
Okay.
Okay.